All right, so we're starting off in section 3.6. So the first thing that I want to talk about, or want to ask, or want to say, why would we want to sketch curves? What did you say? What did you say?
He said it helps you visualize.
It helps you visualize. So that I like that to visualize. Okay, yeah.
We have some curve sketching techniques that can allow you to go from derivatives to functions to integrals. And
Right. So you have a technique, and you also, it helps you understand the relationships between different operations on a function. So I'm going to say, for that one, I'm going to say it helps to build your intuition about functions, how these things are related. So that's good, and that's really a big part of what we want to do. The way I look at it is when if we can build our intuition about functions. What do they look like? How do they behave? That's a big part of what we try to do. If we can gain some intuition, it makes our work a little easier. So that's good. Any other? Why else would we want to sketch them? What?
Kind of on the same tune as the last one, it can give us different information regarding the relationship of the function to its first and second derivatives by means of the inflection points and critical values.
Information about function. We can find intercepts, we can find minima, we can find maxima, we can find inflection points, we can talk about the end behavior. We'll talk about another thing that we'll get a nice reminder of also. Anything else why we'd want to do it? I think we're missing the biggest reason. It's fun. It's great to be able to draw pictures in math, I think. All right. Now, one of my goals for this first bit is not that we're going to be experts at sketching curves, but that we're going to get back into practice of doing some math, taking derivatives, doing some algebra, remembering some stuff about how these things work. So, I'm going to say why. Up here, why we do these things. Our tools. We have a large toolbox at this point after the amount of algebra and calculus that we've studied. So what are some of the tools that we can use to help us if we have a function relationship? What are tools that will help us sketch that function, sketch a graph? Yeah. Pencil, yes. Okay, so mins and maxes. And let's drill down a little bit here. Mins and maxes. What tells us about mins and maxes? Derivatives. We were going to take derivatives. Yep. Zeros. Intercepts. Awesome. And we don't even necessarily need calculus to do that. Sometimes it can help to do things, but this is zeros and intercepts that we spend a lot of time in algebra, and we spend a lot of time in pre-calc finding different ways of finding zeros and intercepts of various kinds of functions. That's one of the big focuses of pre-calc. Yeah. Either one.
End behavior.
End behavior, yes, nice. And end behavior, what is it? What's another way that we can think of end behavior? What's end behavior related to? Limits, right? Oh, now we have, since we're talking about limits, what else does that bring up? Asymptotes. So limits and asymptotes have some relationship. Anything else? Yeah.
You can find the intersection between two functions.
Intersections. If we can think of a function as two functions that are set equal to each other, so we can find intersections. Anything else? Any other ideas? I thought of a couple others that I will add. Domain and range. So kind of non-calculus based. So what's the domain of the function? What's the range of the function? Are there some limitations there? Sometimes it's difficult, but sometimes we can see symmetry. We can take advantage of symmetry. We can see if a function's even, odd, that kind of thing. What else did I? Oh, one other thing. A couple of other things. What about things like sines and cosines? Periodic. We could take advantage of. I'm going to say periodicity. So if it's a periodic function, that's going to give us some information about the sketch of the graph. Yeah.
You do translations from graphs, you know.
Oh, sure. So like transformations of things we know. So that can simplify. We could maybe work with a simplified function and then say, well, this one's just a translation, or this one's a reflection. So that definitely can help us out. And there's one kind of, I would say, an overarching thing that helps us out with all of these is, and we continue to work on it, is just familiarity with, I'm going to say, families of functions. We know what exponential functions look like. We know what logarithmic functions look like. We know what more or less what polynomial functions look like. So that familiarity with those kinds of functions helps us sketch things that involve those kinds of functions. And that relates to what Kevin said, if we can think of it as a transformation. So all these things we can bring into play when we sketch functions. So what I would say in general. Now all of these you can use. So I'm going to put over here in this column. My handwriting gets worse over the summer because I don't write as much. But when I say it gets worse over the summer, don't expect it to get a lot better. So you know. In general, I would suggest, and these aren't hard and fast rules, just my suggestions. I would say look at the domain and the range. Just be aware of any restrictions in the domain, and be aware if there are any restrictions that because of the form of the function that the range only takes on certain values. I would say look at the intercepts. Look at asymptotes. Our asymptotes are usually pretty easy to find for most kinds of functions, and possibly, depending on the function, symmetry. And then now we're going to look at the calculus piece to talk about our mins and maxes, I said derivatives here. What are we looking for? What do we call those things when we're looking for those mins and maxes and inflection points? Where do extrema possibly happen? Critical points. We're going to look at our critical points. So we find our critical points. And our critical points, where do our critical points happen? F prime. I'm going to say an F double prime because we're also looking for inflection points. We're looking for where F prime, F double prime, 0 or undefined. And from this, just as a subtopic here, we find from our critical points, we find whether they're extrema or inflection points. And then we can sketch a decent sketch of the graph if we do these things. So the homework, what I'll say about the homework, there are a lot of graphs, a lot of functions there. So I don't expect that you would do all of those. I would say try a couple, at least one of each kind. So there's kind of some polynomial kind of functions, there's trig functions, there's some rational functions. So I would do some problems. But if you did every single one of those, it would be a lot of work. But there's quite a variety of types of problems. All right, so I want to go through an example with a function, and then I want to give us a reminder about another kind of function that's related to one of the things that we talked about here. So are we good with this information? Is this everything that we got it all in our head? All right, so let's look at an example. We want to analyze and sketch a graph of f of x equals 4x to the 1/3 plus x to the 4/3. All right, a couple of things that we can see right away here. What's really easy to see? What point is this function going to go through? 0, 0. We can see that really easily. So we know that we have an intercept. I'm going to write over here, f of x equals 0 when x equals 0. So that's really easy to see. So could it possibly have another x-intercept? Yeah, let's factor it. I love that word is a great word. Factor. Let's factor it. F of x. Now, I'm not necessarily going to, when we start taking derivatives, I'm going to take the derivative of this. I don't want to take the derivative of the factored one. So I'm going to factor this as x to the 1/3 4 plus x. All right, so now we can see f of x equals 0 when x equals -4. And this is just how I set this up. You may have a more organized way of, like a way that you like to do this. This is just the way I set this one up. So you don't have to do it exactly like I do. All right, what should be our next? What do you think our next step should be? First off, any restrictions in the domain or the range? No, this one's a relatively nice. And what does this function kind of look like? Kind of looks like a normal polynomial, right? Sort of. We just have rational exponents instead of integer exponents. So just off the top of my head, I'm going to guess that it kind of looks like a the graph is going to look like the graph of a polynomial. You know, it's going to do something like that, just because of the form of the graph. So that kind of relates to what Kevin said, not necessarily a translation, but we can recognize the kind of function that it is, sort of. So using our intuition. All right, so what do we want to do next? Let's take a derivative. We're in a calculus class. Let's take a derivative. F prime. Now, that reminds me, I have a friend that has a saying, when all you have is a hammer, everything looks like a nail. So we don't always, because we're in calculus, we don't always take a first derivative, but that's pretty good place to start. All right, so I'm going to take a derivative. So what's going to be the derivative of this thing? Whoops. Plus 4/3 x to the 1/3. Okay. And let's factor this one again, just because we have a common term here. So I'm going to say that equals 4/3 x to the negative 2/3 times 1 plus x. All right, so now we're going to look for, we can find our first pair of critical points. So f prime equals 0 when x equals negative 1. So that's a critical point. And what else do we see? What happens at 0? Undefined, does not exist. F prime So what's going to happen at x equals 0? What's going to happen at 0, 0? Something special happens, right? Definitely something special happens. But when our first derivative is undefined, what do we guess is going to happen? Possibly a vertical slope or a cusp. So when our first derivative, our slope is undefined, we could have a vertical tangent. So vertical tangent, or we could have something really crazy happen. We could have a cusp where there's no slope, no tangent, not a unique tangent. All right. So now we have a couple of critical points here. All right. What's our next step? Another derivative. So to do the second derivative, I would take the derivative of this, not this. And this, now we start getting it. This one's not too bad. When you start having to do quotient rule and that kind of thing, then algebra gets more interesting. When I was in Calc 1, I hated the quotient rule, so I never used it. I always wrote it as a quotient as a negative exponent, and then I would do the algebra to simplify it. I don't recommend that. Just so you know, quotient rule is way better. All right, so our second derivative, what do we get? 8 plus 4/9. All right, I'm going to say right away that this class is much better at arithmetic than my class last year. All right. And I'm gonna factor this also. So I'm gonna factor this to 4/9 x to the negative 5/3. And I'm gonna write it as negative 2 plus x. So factor that just to find our critical points more easily. All right, and what do we see here? F double prime, we're looking for other critical points, equals 0 when x equals 2. So that's another critical point. And what else happens? We get an undefined second derivative when So I'm going to say dne when x equals 0. So we definitely see something interesting happening at x equals 0. All right. So what? Now that we've done this, what do you think our next step should be? Find our max, mins, and inflections. So I know Ms. Hine likes to make the little chart. That's a really nice way to visualize this. So you make your chart, find the sign plus or minus of your first derivative, second derivative on either sides of your critical points to help you sketch your graph. What does Ms. Hine call it? Sign chart?
Yeah, we had a little like a rectangular grid where its first derivative is greater than 0, first derivative is less than 0, and then below that, the second derivative is greater than 0, or the first derivative, or the second derivative is less than 0.
But
and it gives you all of the possible.
Right.
First derivative test, second derivative test.
So you can. The way I usually do it is I just make a number line. This is the way I do it, and then I just mark my critical points. So what are my critical points?
1, 2,
Let me figure out what I'm so we got -4, -1. What else? 0. We have a 0 and a 2, right? So over here, when x is this is just the way I do it. You don't have to do it this way. F prime. Positive or negative? Let's look up here. This is F prime. Positive or negative when x is smaller than -4? Positive? So when x is smaller than -4, so x is -5, this is going to be negative, right? And this is going to be negative, right? Negative?
Is it positive? Yeah. I'm positive.
Is it positive?
Yeah, it's positive.
You could take a cube root, so yeah, it's positive.
Squared, and then you take the cube root, right? So it's going to be positive, right?
Overall,
Oh, overall it's negative, right?
It is negative.
Numerator of the fraction first.
Yeah, I said this. We said this was going to be negative.
No, on the x to the -2.
It doesn't matter. Doesn't matter. So f prime, and I'm going to say f prime equals negative, and f double prime, and this is just the way I do it to make these charts. F double prime. So here's f double prime, negative or positive. Is this if x is -5? Is this going to be negative or negative or positive?
That's negative.
This will be negative, and this will be negative, right?
Positive.
So positive. All right. Between -4 and -1, f prime. So here we are between -4 and -1. So say -2. This will be negative. This will be positive. So negative. F double prime. Still, this is negative. This is positive. Or is this negative?
That's negative. They're both negative.
They're both negative.
Positive.
So the second derivative is going to be positive. Between -1 and 0. That's positive, and this is positive. Yeah? Right. So we switched this, we had a sign switch here. And f double prime between -1 and 0. It's going to be positive, right? So what do we see happens at -1? The derivative changes from negative to positive. It's concave up. We have a minimum there, right? At x equals -1. And here we're still going downhill. We're still going downhill here. So between 0 and 2, f prime. Right, so this is going to, f prime is going to be positive, right? We're putting a positive number here and a positive number here. F double prime, second derivative. Negative. This is going to be positive. This is going to be negative. So negative. So what happens here at 0? Inflection point, and what is our tangent? What happens to our tangent? Vertical tangent, right? Because it's our derivative is positive. We're still going uphill, so we're going really steep uphill. And between 2 and infinity, f prime is positive. F double prime is positive. All right. Now we can sketch a graph, more or less. My graph sketches, if you can get your graph to look at least as good as mine, you're fine. And mine usually don't look that great. So where is our intercept? Was that at -4? Oh, that's not a critical point. We didn't need to do that one. That was just an intercept. So our graph does this. Here at -1, 3, if we plug -1 into our function, we'd see that point's -1, 3. It goes up, and I need to get this going like this. So we have an inflection point there at 0, 0. And then at 2, we have another inflection point. So it kind of goes like this, and then up. And where it changes, let me make that a little better. There we go. Where it changes is the point, if we plugged our value in, 7.5. And this is for 0. -4, 0, sorry.
Is that -1, -3?
Yes, it is -1, -3. Thank you. So there's a rough sketch of that graph. And just a reminder, when I say, if I ask on a quiz or a test, find the points, I'm talking about the x and the y coordinate, not just x equals 5. Find your points. Point is x and a y. All right. Isn't that fun? What time do we get out of here? Oh, 19. I want to give you, so we're good here. And I'm sure that when you do the process, it goes faster than what we did here because we were doing it all together. All right, I want to give you a reminder about one thing really quickly. What if we were sketching a graph? We're not going to go through the entire process for this one. For f of x equals x to the third over x squared plus 1. What is going to happen with this graph? We're going to have Paul's going to have the numerator and denominator 0 at the same time. The degree of the numerator is 1 more than the degree of the denominator. Someone's going to say it. Yes, the limit is infinity.
Oh yeah, 3 halves.
That's when they're the same, right? We know it's What's that?
Is the limit not? It approaches
What?
infinity.
Yeah, yeah. What happens with rational functions? What often happens with rational functions? What do they have? Often. Asymptotes. We're going to have an asymptote here, but the degree of the numerator is 1 more than the degree of the denominator. What kind of asymptote?
Horizontal.
No, that's when... Somewhere between horizontal and vertical. Slant asymptote. How do we find the slant asymptote? No, that's when they're the same. That's long division, yes. All right, so we need to find the slant asymptote by doing long division. So I'm going to divide x squared plus 1, yes.
You said it's a slant asymptote because the degree of the top is 1 bigger than the degree of the bottom?
Yes.
Okay. What's the other rule?
If they're the same, it's a horizontal asymptote at the ratio of the leading coefficients.
Okay, so if I had 3x to the third over 2x to the third, it'd be 3 halves.
3 halves, yes. Y equals 3 halves.
And then with this, do you still apply the normal rules that go with that rule, the one where it's like that has a asymptote of infinity or whatever, for the, or one, I can't remember, for the end behavior, it still behaves normally for the end behavior,
Yeah, yeah, yeah.
regardless of the slant asymptote.
Yeah, it's still going to infinity.
Yeah, yeah.
It's just how it goes to infinity, right? So we're going to divide x squared plus 1 into x to the third plus, you could write 0x squared plus 0x plus 0. And what do we get? X. And then we subtract, right? But this should be an x to the third. And we get a 0x plus minus, we get a minus x there, 0x minus x. And we can't go any further. So our slant asymptote is y equals x. This is what gives us our slant asymptote.
So you don't deal with the remainder of this?
No, we've just go. Yeah, that. Well, what this tells us is that x to the third over x squared plus 1 equals x minus x over x squared plus 1. So this, the limit as x approaches infinity of this is 0. So we're just left with this eventually.
So you should evaluate that, the remainder, and make sure that it doesn't actually go to 0, otherwise you wouldn't.
Well, the way we know, we can't divide x squared into x now, so that tells us we're done. All right, so you will have some with slant asymptotes. All right, our homework. Again, pick a variety of problems.
What? We're going to the... Mr. Beaver, the homework's online, right?
Yes, and it's also written on the board on the side there.
Kevin, what's his score? 69.
There is one of the homework problems that is a trigonometric function. There's an example in the book that talks about the trigonometric function, so you might want to look at that. You don't have to do all of them, no. If you did all of them, that would be a huge amount of work.
That would be a huge amount.
Do a variety.
Should we just do half? Do one
Yeah, do one of every kind. Pick a few that look interesting. Have a good weekend. Yeah, don't do any.